Right, then I don't need to present you. Maybe you think about other questions after the second talk. Dear video.
Okay, so hello again. It's me again, Henning. This is my second talk at this year's SDR Academy. In this talk, I will present to you how you can easily modify your Pluto SDR in order to MIMO operations, means multiple antenna, multiple input, multiple output operation. So using multiple antennas at the same time. Yeah. First, a little motivation, and then I will go into the technical details. Motivation. I guess all of you know, or at least most of you know, that there is this very famous ADALM-PLUTO, so analog devices active learning module Pluto, which is a software-defined radio based on the Xilinx Zinc platform, combined with a high-performance broadband mobile radio front end. And it's been around for a few years already, this Pluto SDR, and not long time ago, last year or the year before that, they made a new revision of the Pluto SDR. And when you read about the details of this revision D, Pluto SDR, you will find that actually this Pluto SDR has the second transmit and receive connectors available on the PCB. It means you can easily modify your Pluto SDR to do simultaneously multiple antenna transmission and reception. And those of you who watched my last year's talk on multiple antenna stuff, and also the presentation I gave on the stuff we did at university 10 years ago, will find out that you can do a lot of interesting stuff when you do have multiple antennas at hand, when you receive multiple replicas of the same signal, or if you are able to use multiple transmit signals in order to achieve some kind of beamforming, for instance. So this Pluto revision D has the second transmit and receive paths routed out to these UFL connectors. These are the little tiny connectors. Some of you know these from your Wi-Fi card in your laptop. This is how this external antenna is usually connected, or how the antenna in the lid of the laptop is connected to the Wi-Fi card. Little tiny fragile connectors. These are here on the main top side of this PCB here, of the Pluto SDR. And you can buy standard pigtails and have them, say, routed out. You have also additional connectors for clock input and clock output. This can be interesting if you want to synchronize more than one Pluto SDR, or if you are planning to use an external clock, for instance, a GPS disciplined oscillator, for instance, then you would also can make use of this external clock input here that's shown in yellow here in this little picture. Yeah, of course, the Pluto is still advertised as a, say, single input, single output device. That's what they actually explicitly state on their webpage in the wiki, that the second RX RTX is just a bonus. It's not tested during production. So if you have bad luck and it doesn't work, say, yeah, bad luck. So let's give it a try, because it's not very hard to enable the second input and second output. First of all, this is then how it looks like when you added the second transmitter, second receiver, and the clock input. You can just drill holes into the little plastic part here where the SMA connectors are located, and by doing so you can easily, say, have 5 SMA jacks here on the Pluto SDR without it doesn't get too fiddly to connect the cables, even with this 5 connectors on this side of the Pluto here. So this is why I wrote, you should always add the ref clock input, because when you have it already open, just use the opportunity to add this reference clock. Yeah, how to enable it by software? It's actually not more difficult than extending the frequency range, because the stock Pluto SDR is only specified from 325 to 3,800 megahertz because the chip that's actually soldered on the PCB is this AD9363, but of course this is just a binned version of the AD9361, which is just selected for linearity and other stuff. This is how you can easily just by setting a variable modify your configuration such that you can first of all use the extended frequency range from 70 to 6,000 megahertz and also enable the second RX and second TX. It's explained in all detail on Analog's wiki page, as you see here on the slide. So just follow the instructions and then you will end up with a Pluto SDR which has MIMO capability. Yeah, but now the big question is, how do I actually use now this second TX and second RX in GNU Radio? Because the standard Pluto SDR source or sync block only has one output or one input, respectively. In order to come over this, seemingly it's a restriction, but actually it's not, because what you need to know is that the Pluto SDR actually is a scaled down low-cost derivative of the so-called FMCOMS3 add-on board by Analog Devices for the Xilinx Zinc FPGA evaluation boards. This FMCOM3 board is an add-on board with an FMC connector. You can plug it onto a stock evaluation board for the Zinc, either the ZC702 or the Z board. And then you end up with a system that's well supported by Analog Devices. And the blocks that you would use in such a system would be the FMCOMS 234 blocks. You see these on the right here, and you can easily check set the receivers enabled, RX1, RX2, and also for the transmitter side, TX1, TX2, and then you will automatically get a second, say, port here where you can wire your other blocks to. And to be precise, I don't know who of you already know this, but the stock, say the standard Pluto SDR sync and source blocks in GNU Radio are actually just wrappers around these FMCOMS 234 blocks. For instance, if you look at the source code, C++ source code for the for GNU Radio 3.8, and you look at the source for the Pluto source, you see basically it's just instantiating the FMCOMS 2 block with just some values hard-coded, yeah, with just a second output just disabled, set to false. Yeah, so basically the Pluto source is actually under the hood. It's an FMCOMS 2 source. So why not use it directly afterwards? The GNU Radio 3.10, it looks like this. So even it went a step further, because if it's just a wrapper at all, a C++ wrapper in on the side that you saw before, then you can just maybe directly use a Python wrapper. Yeah. So in GNU Radio 3.10, basically when you pull the Pluto SDR source block into your flow graph in the resulting Python code with just some variable just hard-coded to certain values. Yeah. So this is then how this looks like. Maybe you noticed that I mentioned GNU Radio 3.8 and GNU Radio 3.10 because there is no GRIIO for GNU Radio 3.9. Means there is no official way to use a Pluto SDR or an FMCOMS 2 add-on board with GNU Radio 3.9. I don't know why. I searched the internet, I found nothing, so I made the effort and ported the 3.8 blocks to 3.9, and you can get it on my GitHub if you're interested. If you want to use a Pluto SDR on GNU Radio 3.9, you can find the out-of-tree block set here on my GitHub and compile it yourself. It's not that hard. It should work out automatically if you have done this before. Yeah, so you see the integration is really not that hard. And what you can actually then do using these blocks, I have presented a quick and dirty demonstration for that, means frequency modulated continuous wave radar. So how does it look like? I built two antennas, means from little delicious wafer rolls. I built two antennas for 13 centimeter, and I bought a splitter of Amazon. It's a standard Wilkinson divider, I assume. And what I did was I took the TX1 output of the Pluto SDR, split it into the transmit antenna and into the second receive path, so means the one that I added using this little pigtail. And of course, the primary receive input was connected to the other, the receive antenna, basically. And the rest is just software, means all the attenuation and the gain and stuff like that. You can easily do this in GNU Radio yourself. You don't need any additional hardware for that, amplifiers, attenuators, or the like. It's highly integrated. Yeah, now you plug all this together and you get this very quick and dirty flow graph here, which looks as the following. We have the FM comms source, means just the two-channel receive Pluto, basically. We treat these outputs, say, individually regarding the spectrum display, and but what we do then is we combine the real parts of these two outputs into a virtual complex signal, just in order to get an XY display on the virtual scope using this QT constellation sync. You will see in a minute what it means. Then you can basically directly see the frequency shift between the transmit and the receive antenna by doing so. Yeah. And what you do actually, we subtract one frequency from the other, means we feed these two signals into, say, a virtual mixer down converter here, means this block here will give us the frequency difference between the two signals, or the phase difference and the frequency difference. After low pass filtering, you get then a signal. You can see this in a minute how it looks like. The phase and the instantaneous frequency will give you some hint about the distance and the Doppler shift. The frequency modulator calculates the Doppler shift, and the taking the argument will give you the instantaneous angle, which is somehow proportional to the delay between these two antennas. Yeah, there is some smoothing going on here, moving average filter, and this here is something that I wrote myself, sliding maximum block. You can also find it on my GitHub. This will just take the maximum in a sliding window and then output it. This is because these little Doppler glitches will be quite short, at least in the examples that I will that I have tried, and I will show you in a second. So that means you need to somehow make them longer in order to be able to display them. And this will then, this is what I already told you. This is what the blocks do. They do this, say, frequency comparison between the transmit and the received signal. And one point I'd like to point out is you have to take care of the sampling rate, because after all, you're just limited to USB 2.0. That means, and we're doing full duplex. This is what you see on the top right here. Yeah, I'm generating a frequency modulated signal in software and transmitting it via USB to the, say, transmit part of this Pluto SDR. This means we're doing full duplex in the MIMO mode. Means we have to take care that the bandwidth doesn't get too large. So this is why I was restricted to 960 kilosamples per second here, which works okay in my application. I didn't get any packet losses in that case. Yeah, and then this is how this looks like when you start the flow graph, and this is where I'd like to switch over to the live demonstration. This is the GNU Radio block set that you just saw before. Now it's shown live in your screen. And now let's start this flow graph here. And now you get some live picture like this. And maybe I can now take this setup and show it to the camera. And what you basically see is when you now here when I move my hand in front of the antennas, you see that the phase shift between the transmit and the receive signal, actually changes. And you can directly see that the modulo one wavelength, I can measure the distance between the antennas at my hand in this situation here. And if I scroll a little bit down, see here bar graph that will somehow estimate the distance measured in radians, because it's actually the angle from my hand to the antenna setup. And on the left here, this is the demodulated signal. Yeah, this is just the say the received signal demodulated by the reference signal. This is how you can interpret this. And if I now move my hand a bit more quickly in front of the antenna, you see that there's actually a Doppler shift. It's not much, but a little bit is there. And this is what this lower bar graph actually measured. I can't tell you actually the units. It's arbitrary units, but it somehow shows you that if there is some Doppler shift, the bar graph will show you at least the order of magnitude in which this shift is. Because there's some glitching, because it's not just only one reflection, and it's not very good at separating different echoes, but it's just a quick and dirty proof of concept. And I think it very nicely demonstrates the basic principles of wave propagation, at least in this case, and it somehow illustrates the principle of a radar system in this case. Yeah, I'm now returning to my slides. This is the live demonstration that you just saw, and I'm already at the conclusion of my talk. So what's the points that you should take with you from this talk? Point one is modification is really not that hard. If you are the proud owner of a revision D Pluto SDR, you should really do it. You should try to modify it with the additional transmit and receive connectors. The pigtails are not expensive. They're like €5 a piece, or something like that. Just try it. Because you don't need any additional software, you don't need to pull anything from the internet, except if you use GNU Radio 3.9, of course, then you need to use my repo. But if you use 3.8 or 3.10 or higher, you can just use stock GRIIO blocks in order to do MIMO. And of course, now you can able to do it, say from 70 megahertz up to 6 gigahertz. Now I say to you, do MIMO in all the bands. Yeah, 2x2 full-duplex MIMO. I guess 20 years ago, researchers dreamt of a device that was that affordable and would be capable of doing 2x2 MIMO in full duplex in real time. So really use it, employ it, make your own experiments, and maybe you can give a presentation next year on what you did interesting with the MIMO enhanced Pluto SDR. Yeah, that was my talk. Thank you very much for your attention, and of course, I'm open for questions in the Q&A.
Yeah, thank you very much. Oh, I wanted to build a radar myself for such a long time. Now I know how to do it. Great, fantastic talk. So we have 8 more minutes. That's enough time for a lot of questions. What are your questions? Has anyone of you tried to build? Ah, yeah, there's a question. Okay.
just a practical questions. Question. Can I order the revision D, or how can I be sure that I don't get old revisions that are still in stock?
So if you order at the large retailers like Mauser or DigiKey, you will pretty sure get a revision D, because they don't, I guess they sold all the old revisions years ago. I don't know how it is with other, say, vendors. It's not a guarantee. Maybe they will charge you extra add-on fee to make sure if you want to get revision D in that case. But if you order it DigiKey or Mauser, you will pretty sure get revision D.
Thanks.
Okay. Any more questions? Has anyone of you tried to build something like that or work with reflections? Nobody yet? Have you tried to assess your own signal? Yep. How was it?
I was not using a Pluto.
What did you use?
USRP.
USRP? Okay, that's a cool platform, but a pretty expensive platform. How much does it cost in the meantime? Too much. Yeah, well, that's an expensive platform. Yeah, true. Any more questions? We have an ADALM-PLUTO right here. There's one visitor.
It's just revision E. I was just checking. It's a very old one.
Okay.
2-3 years back or so.
Okay. Okay. I don't have that one. I have a couple of others. Over time, you collect an entire zoo of SDRs over the years, but I think it's still worth considering a new one from time to time. So, anything else we would? Yeah, there is a question. No question. Okay. Okay. Yeah, there is an online question from the chat. Let me just have a look. So our colleagues from the European GNU Radio Days are asking, excellent demo for the second channel for sampling the LO difference. Great. Well, it's a comment, more a comment than a question. The second thing is I would use a 20 dB coupler rather than a splitter to TX as much power as possible without damaging, saturating the RX. Yeah, that's a comment. Have you considered that?
Yes, I actually have, but I guess I have to admit that the Amazon Prime delivery was too tempting, and I wanted to get it running the next day, so I ordered what was available. And then of course, I know that I lose half of the transmit power in the splitter, but actually I am planning to build a power amplifier anyway, to add in between the splitter output and the transmit antenna. So let's see how that figures out.
Okay, that's interesting. Well, good then. No more questions from anywhere? Then I would like to thank you. And thanks for contributing. Thanks for coming in. And
thanks for having me.
Have a nice Saturday afternoon in sunshine up there in Bremen. Thank you. Thank you very much.
I will. Thank you.